What's up, nerds? Here we have a tension challenge question. In this question, we have a 10 kilogram mass and an 8 kilogram mass on a table connected by a rope exerting 47.6 newtons of tension. They're connected by a second rope to another object hanging off the table. The coefficient of friction between the table and the masses is 0.45. So, before we do anything, we need to draw all the forces so we can understand this problem. We need to really understand what's going on before we can start solving it. The first thing I think when I look at this problem is that we're going to have a gravitational force pulling down here. Let's call this Fg1. Fg1 is what I would call the winning force of the system. Of the whole system, that is the strongest unbalanced force. It's going to cause all the blocks to move and be dragged in that direction. So downwards for M1, and M2 and M3 are going to be pulled to the right due to this gravitational force. Now, of course, when it's pulled downwards, there will be a tension force pulling back on that. Let's call this Ft1. And of course, this is the same tension force, also Ft1, because the tension is constant within one rope always. So this is one rope going through a pulley, and within one rope, you have to have the same tension at all points within a rope. Now, we know that this will push downwards into the table. Let's call that Fg2. Let's call this Fn2. By the way, I'm using dashes to signify when forces are equal to each other. So the Ft1s are equal, so I did one dash. Now these are equal, but they're not equal to the tension force, but they're equal to each other. So I'm going to do two dashes to signify a separate pair of equal forces. Now we know here, let's call this Ft2. This is a different rope, so it will have a different tension value. And we know Ft2 in both cases, it was given in the question as 47.6 newtons. So that is both of these values. And I'll do a triple dash because those are equal to each other. And then we're on to M3. Now M3 is heavier, so I'm going to draw a larger gravitational force and a larger normal force. And the last thing is we know there's friction forces because we saw in the question there was a coefficient of friction. That means that there's going to be a friction force pulling backwards on both of these as they try to slide off the table. Oh, and I meant to do a quadruple dash on these ones. I don't do a quadruple dash very often, but the situation calls for it. Now, here's all the forces. Maybe these arrows are a bit misleading. I'm trying to say that this tension value and this tension value are equal to 47.6. Now, let's look at what we're asked to find. First, we're asked to find the acceleration of the masses. Then we're asked to find the tension in the other rope, so that will be Ft1. We already know Ft2, so we're asked to find Ft1. What is the mass of the object hanging off the table? And then lastly, what is the most mass that could hang off the table without moving, so without sliding off the table, or without sliding M2 and M3 off the table? So, part A. Find the acceleration of the masses. I want to look at what do I know and what do I not know. So thinking of things that I don't know and I can't find very easily. I definitely don't know Fg1 because I can see in part C I'm asked to find the mass of that. So until part C I don't think we'll know what that is. I also don't know Ft1 because in part B I'm asked to find what is Ft1. So I don't know what that is yet, and I probably won't find it in part A. So I don't know any of these forces on the right. If I want to select a system that will allow me to find the acceleration of the masses, I need to pick somewhere that I only have one unknown. And the only unknown can be the acceleration. So the only place where the only unknown is acceleration is here. Now I can pick my system to be anything. I can pick my system to be all the masses, or mass 2 and mass 3, or just mass 3, or just mass 2, or just mass 1. As a physicist, you can define your system however you want. Now I'm choosing to ignore mass 2 and mass 1 and look only at mass 3. So this is my system for right now. And I can change it later. But I'm going to start by looking just at mass 3 because I know a lot of information about mass 3, and I think it will allow me to find the acceleration. So let's work over here. And I want to do a FNet statement for mass 3. Now, an FNet statement I also call a winners minus losers statement. So what's going to happen to mass 3 is it's going to get dragged to the right. It's going to accelerate to the right. And that means the right force is the winning force. So Ft2 is the winning force. Now, fighting against that is the losing force, which is FF3. And that's equal to M3 times A, because we're looking at M3. So here is my statement that I got from looking at the diagram. So this is my FNet statement, my winners minus losers statement right here. And if I solve this, then I can solve the problem. Now, I need to rearrange this to find A, so I'll divide both sides by M, and I'll get Ft2 minus FF3 over M3 equals to A. And before I continue, I need to find what is the force of friction. So let's do a little aside here and find FF3. So FF3, well, any force of friction is equal to mu Fn. Right? That's the definition of friction. Now coming back over here, you should notice that Fn and Fg are balanced with each other. So in this case, and in any case where we're sitting on flat ground, Fn is the same as Fg, which is the same as mg. So this is equal to mu m3 times g, which is equal to 0.45 is the mu given in the question, m3 is 10, and g is 9.8. And so we find FF3 is equal to 44.1 newtons. Okay, so let's carry on with our problem here. We find A equals 47.6 is the tension that was given to us. 44.1 is the friction we just found. M3 is 10. And we find that the acceleration is 0.35 meters per second squared. Okay, so that means that the block hanging off the table is accelerating downwards at 0.35. They all have the same acceleration because they're connected by ropes. So and then M2 and M3 are pulled forwards to the right at 0.35 meters per second. Okay, so let's clean some of this up and we'll look at part B. Find the tension in the other rope. So I'm thinking again, what do I want my system to be? Well, I still don't know Fg1 down here. I'm still uncertain on this one. So I want to avoid that. I want to have only one unknown value, and I want that unknown value to be Ft1. So I can't pick my system to be here, for example, because then I would have two unknown values. So I'm going to pick my system to be just mass 2. So looking at just mass 2, if I make an FNet statement and solve it, I can see I will have only one unknown value, which is Ft1. I think I have everything else, or I can find it, such as friction here. I know I can find this. And Fn, I know I can find this. So I really just have the one unknown value, which is Ft1. So let's go ahead and make an FNet statement for part B, looking at M2. So picking M2, my winning force that is pulling the blocks forward, that is accelerating them forward, is Ft1. My losing force, I actually have two losing forces pointed the other way. You can see here, trying to slow the block down is Ft2. and FF2. Those are both pulling back the other way. And this is equal to M2 times A. And looking at our situation here, we're going to have to rearrange to say FT1 equals M2A plus FT2 plus FF2. So I'm adding this to this side and adding this to this side, and now I've isolated FT1. Okay, now I know M2 and A and FT2, so all that's left to do is quickly find FF2 here. Let's double check what this is, or let's calculate what this is so that we're ready to solve our problem. So FF is equal to mu Fn, Fn2 in this case, and as we already discussed, that's equal to mu times m times g, because again we see that the vertical forces are balanced. So Fn equals Fg, Fg equals m times g, and we end up with this situation where we have 0.45 times mass 2, which is 8, times 9.8, and we find FF2 equals 35.28 newtons. Okay, and now we're ready to solve part B. So FT1 equals M2, which is 8, times A, which we found before, plus FT2 is 47.6, plus FF2, which we just found, is 35.28, and we find FT1 is equal to 85.7 newtons. Okay, so the tension in that rope is much higher, which makes sense if you think about it, because the first rope on the left is pulling only M3, but the second rope is pulling M2 and M3, so it needs to have more tension. Okay, let me clean up my workspace a bit here. And part C, sorry, not lastly. Part C is asking for the mass of M1. So, I'll just let you know here that you have two options for your system for this one. You could pick the entire thing as your system because this is now the only unknown, or you could pick just M1 as your system. Now, I think M1 is just going to be a bit simpler, so I'm going to pick that one, but if you looked at the entire system, you would still get the right answer. So for part C, I'm looking at the net force statement for M1, the winners minus losers statement for M1. And I have here Fg1 as my winning force, and Ft1 as my losing force, equals to M1A. There's no friction, of course, because it's not touching the table. It's hanging in the air off the edge of the table. And I can now find M1 by dividing both sides by A. And I find M1 equals Fg1, which is, oh, no, sorry, I've made a mistake here. This is a bit more complicated. This is M1G minus Ft1 equals M1A. And sorry, the reason it's a bit more complicated is that we have two M1 values. We have M1 here and M1 here. So we're going to have to do a bit of algebra. So what I'm going to do is I'm going to add Ft1 to both sides, and I'm going to subtract M1A from both sides. So I'll get M1G minus M1A equals Ft1. Okay, now I can factor out an M1, and I'm left with G minus A equals Ft1. And I'm going to divide both sides by G minus A, and now I've solved for M1. So M1 equals Ft1, which we just found is 85.7, divided by 9.8 minus 1.63. Excuse my dog if you can hear the barking, my apologies. And we have here M1 is equal to 9.1 kilograms. Okay, so that is the amount of mass that is hanging off the table given everything else we found. Given the amount of tension and the acceleration, that must be the amount of mass hanging off the table. Okay, lastly, we're looking at part D. What is the most mass that could hang off the table without moving? Now, obviously 9.1 kilograms is what the real mass is here, and we found that that accelerates it slowly at 0.35 meters per second squared. So if we had less mass, then the friction would just completely stop the mass. It would be stationary. So let's take a look. What should our system be for us to find the least mass, for A to be 0? Well, why don't we look at the entire system? If we look at the entire system, then the tension forces will cancel because they're pointed both directions. So we have this as our winning force, and the losing forces are actually just the two friction forces. Okay? All the highlighted forces, these are the forces that are pushing and pulling against each other to accelerate the system. Everything else is balanced by another force. You can see the tension forces are balanced with each other. The normal forces are balanced with the gravitational forces. So let's write our winners minus losers statement for the whole system. We find for part D that we have Fg1 is the winning force minus Ff2 minus Ff3 equals, well, we're now looking at the whole system, so we have to look at all the masses together times A. Now if A is 0, we actually don't have to look at this at all. And we would find that Fg1 is equal to Ff2 plus Ff3. So some people would actually just start here and not write the statement above. If the friction forces are equal to the gravitational force pulling down, then nothing will happen. It won't move. So we get M1G equals Ff2 plus Ff3. Whoops. And divide both sides by G. We get M1 for the system to not move because the forces are balanced. M1, well, we already found Ff2 earlier, which is 35.28 plus we found friction earlier is 44.1. Sorry, this is Ff2 and Ff3. So adding those friction values together and dividing by 9.8, we find that it's 8.1 kilograms. So if M1 was less than or equal to 8.1 kg, the system will not move. Because if it's 8.1 or less, the friction of M2 and M3 is enough to support that much mass. If it's more than 8.1 kilograms, then the system will start accelerating off the table. All right, thanks for listening. Great job if you made it through the video. I'll see you next time.